Hi guys, welcome back to YouTube channel Chemistry Live UGPG. Today we are going to talk about effective nuclear charge and Slater rule. So this will be highly beneficial for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So today we are going to talk about effective nuclear charge and Slater rule. So consider an electron in one of the atomic orbitals of a multi-electron atom. So here Z is the nucleus and the electrons are in different orbits. So these are the electrons. So the outer electrons are attracted towards the nucleus by nuclear charge. So the electrons will be attracted towards the nucleus. Similarly, the electron will have a repulsion. So, but are pushed away from nucleus by repulsion of inner electrons. So we all know the nucleus is positively charged. So hence nuclear charge. So because of the electrostatic repulsion by other electrons in the same or other orbitals, the nuclear charge felt by this electron will be less than the actual nuclear charge. So this electron is said to be screened from the influence of the nuclear charge, and the reduced charge felt by the electron is known as effective nuclear charge. So the intervening electrons screen the electrons present in the peripheral sp-df orbitals of even the same principal shell to the different extent. So Z effective, that is effective nuclear charge, that is equal to Z actual minus S, the electron shielding. So effective nuclear charge Z effective is the nuclear charge actually felt by an electron. So for the orbital ns, np, nd, nf, so this way Z effective will decrease and the energy will go on increasing. So in multi-electron atom, electrons in the inner shell put a screen of negative charge on the nucleus. So therefore outer electrons experience lesser attractive effect of the nucleus. So the actual nuclear charge on the outer electron experiences is called effective nuclear charge Z star. So Z star equal to Z minus sigma. So here Z equal to atomic number and sigma is screening or shielding constant. So if sigma is known, Z star can be calculated by using Slater rule. The next is variation of effective nuclear charge in periodic table. So the Z effective goes on increasing with increase in atomic number. So therefore the hold of the nucleus on the electrons also goes on increasing as we move from scandium to zinc. So fast transition series. So hence the atomic size goes on decreasing with the increase in atomic number as we move along the series. So in multi-electron atoms there are a number of electrons. Some of them occupying the low energy orbitals tend to reduce the effect of nuclear charge on the electrons present in higher energy orbitals. So this is due to the fact that these orbitals intervene between the nucleus and the electrons in the higher energy orbitals. So this effect is called screening effect or shielding effect. Since the electrons present in the different types of orbitals like S, P, D or F are screened differently, they are attracted to different extent by the nucleus. So the electrons in inner shell act as a screen or shield between the nucleus and the electrons in outermost shell. So this is known as screening effect or shielding effect. So larger the number of electrons in inner shell, greater is the screening effect. So consequently the electrons in the valence shell experience less attraction from the nucleus. So let's talk about what is Slater rule. The extent of screening of an electron by the other electrons in an atom is calculated with the help of some empirical rules known as Slater rule. So these rules are very important, so please listen very carefully. So the various orbitals are grouped starting from the nucleus like 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p. So for an electron in a group of s, p electrons, the value of screening constant S is the sum of the following contributions. No contribution from any electron present in group of orbitals lying on the right side of the group in which the electron for which the S is to be determined is present. Secondly, a contribution of 0.35 from every other electron present in the group of orbitals, say Ns and P, under consideration. So a contribution of 0.30 from the other electron in 1s orbital if the electron for which the S is to be calculated belongs to the 1s orbital. Thirdly, a contribution of 0.85 per electron from all electrons with quantum number n-1, that is electron present in n-1th cell. And a contribution of 1.0 per electron from all electrons present in the n-2th and the next inner cell. So this is also very important. So for an electron in a group of D or F electrons, the rules 2i and 2ii apply as such. However, the rules 2, 3 and 2iv are replaced by rule that the contribution per electron from all the electrons in the inner cell is 1.0. So these are called Slater rule. So now we can summarize here. So orbitals are grouped as like 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, etc. So sigma equal to 0 for electron of nth or higher group n plus 1. So then sigma equal to 0.35. So per electron for rest of the group of electron. So this is most important. Then sigma equal to 0.30 for 1s electron screening another 1s electron. Similarly, this is also important. Sigma equal to 0.85 per electron for all electrons in n-1th group. And sigma equal to 1.0. This is also important. Per electron for all the electrons in n-2 or lower groups. Then finally, in case of electron being shielded of Nd or Nf, all electron lying to the left of the Nd or Nf group, sigma will be 1 per electron. So these are called Slater rule. So the screening power of different orbitals is S greater than P greater than D greater than F. So let's calculate the Z star for the valence electron of Na. So valence electron is 3s1. So this will be grouped as 2s2, 2p6, n-1th and 1s2 will be n-2th. So sigma we can find out as 1 into 2 plus 8 into 0.85 plus 1 into 0.0. So sigma is 8.8. So Z star will be equal to Z minus sigma. So Z is 11. 11 minus sigma is found to be 8.8. So that is found to be 2.2. Similarly, Z star for 10th D electron of a zinc 30. So zinc 30 electronic configuration we write like this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. So 10th electron. So sigma we can find out 1 into 18 plus 0.35 into 9 and plus 2 into 0. So it is found to be 21.15. So Z star equal to 30 minus 21.15. So it is found to be 8.85. Similarly, you can find out Z star for magnesium. So you write first the electronic configuration in this fashion and then you group them to n-1 and n-2th cell. So sigma equal to here 1 into 2 plus 8 into 0.85. For this cell it is 0.85 and for this 3s electron, so we have a 0.35 into 1.0. So it is 9.15 and Z star equal to Z minus sigma. So Z is 12. 12 minus sigma is 9.15. So 2.85. The next is a variation of a Z star in the periodic table. So Z star remains constant in a group except for the first member. So lithium, sodium, potassium, rubidium, cesium. So you can see the Z star remains constant except for first member. Similarly, Z star increases in a period from left to right. So lithium to fluorine. So 1.3 to you can get 5.2. So here are some problems. What is the effective nuclear charge felt by 1s electron of helium atom? So electronic configuration is 1s2 and there is one more 1s electron apart from the electron for which Z effective to be calculated. So screening constant equal to 1 into 0.30. So it becomes screening constant is 0.30. So Z effective will be Z minus S. So 2 Z is 2 atomic number. So minus 0.30. So that is 1.70. Similarly, you can find out what is the effective nuclear charge felt by 2p and 1s electron for nitrogen atom. So nitrogen atomic number 7. So it will electronic configuration is 1s2, 2s2, 2p3. So there are 4 other electrons in 2s and 2p group. So we first find out for the 2p electron. So screening constant will be 4 into 0.35 plus 2 into for this one 0.85. This is n minus 1 cell. So that becomes 3.10. So Z effective equal to Z minus S. So 7 minus 3.10 that becomes 3.90. Similarly for 1s electron it is found to be 7 minus 1 into 0.30. So that becomes 6.70. Similarly, calculate the effective nuclear charge felt by a 3d electron for chromium atom. So chromium atomic number 24. So electronic configuration you can write like this: 1s2, 2s2, 2p6, one group, then 3s2, 3p6, another group, 3d5 and 4s1. So we have to go for a 3d electron. So 3d electron means here 5 electron. So there will be no contribution for 4s electron. So and there are 4 other 3d electron. So Z effective will be 24 minus 0.35 into 4 minus 1.0 of a rest inner electron. So into 18. So that becomes 4.60. Similarly, you can explain a cation is smaller in size than the parent atom. So sodium atomic number is 1s2, 2s2, 2p6, 3s1. So Z effective held by 3s electron, that is the last electron, that is 2.20. And Na plus is 1s2, 2s2, 2p6. So Z effective held by the last electron of Na plus ion is found to be 6.85. So Z effective is less. So bigger in size. So the hold of nucleus on the electron is less. Similarly, you can calculate the Z effective for 3d electron, 4s electron for copper atom. So copper atom atomic number 29. So you can write the electronic configuration and group them like this. So Z effective held by 3d electron will be 29 minus 9 into 0.35 plus 18 into 1.0. So it is found to be 7.85. Similarly for 4s electron will be 29 minus 0.35 into 0 plus 10 into 1.0 plus 18 into 0.85. So it becomes 3.35. Similarly, you can also explain an anion is bigger in size than the neutral atom. So suppose chlorine, atomic number 17. So you can write the electronic configuration and group them like this. So Z effective held by chlorine atom is found to be 6.10 and Z effective held by Cl ion, that is 5.75. So Z effective for Cl ion is Cl minus ion is less. So nucleus would have lesser hold on electrons on Cl minus ion than chlorine atom, hence have larger in size. So similarly, you can have another problem: the transition metal lose Ns electrons fast during ionization. So let's say manganese 25. So electronic configuration you can write like this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. So this will be n minus 1 cell and this is n minus 2th cell. So Z effective by 4s electron is 25 minus 1 into 0.35. Here 1 electron is there, so plus here 13 electrons, 13 into 0.85 plus this is 10 electron. 10 into 1.0, that is 3.60. And Z effective by 3d electrons. So remaining 4 electrons are there. So 25 minus 4 into 0.35 plus 18 into 1.0. So that is 5.60. So Z effective for 4s electron is less. So hence the attraction between the nucleus and 4s electron is less, and it is easier to remove an electron. So please subscribe to our channel Chemistry Live UGPG. This is also available in the website www.chemistryliveugpg.com. So for class 11th and 12th, this is the channel Foundation Chemistry AB. So this is a simple step towards e-learning, making life better. Thank you all for learning.